Okay, this is going to be our sixth and final video on rotational motion. And so for this video, really I'm just going to try and bring some of these ideas together. Most of the video is going to consist of doing one example here. We could do a bunch more examples, but we're just not going to have time, unfortunately, to do too many more. So let's get right into it here. So the idea here is that in the real world, it's often more useful for us to model objects as objects with extent, right? So extended bodies when we're looking at some of these collisions. If we model objects as not point masses but extended bodies, then we can start looking at things like rotation in these collisions. So if we look at a collision of 2 point masses, we can't really have any rotation, right? But if we look at the collision of two extended bodies, we can take into consideration that one or both of them may end up rotating after the collision. And this makes sense if we want to model certain things in the real world. For example, I talk here a little bit about a car collision. If two cars were to crash into each other, a number of the configurations that we could set up for these two cars to crash into each other would result in one of the cars after the collision having some rotation, right? And so we're going to take a look at an example here where we have extended bodies colliding in 2 dimensions. Okay, this is example 10.15 from the text. Rotation in a collision. Okay, so it's basically the same problem. I've reworded it slightly, but it's more or less exactly the same. So suppose we have a disk of mass 0.05 kilograms that has an initial velocity of 30 meters per second. Then we're going to suppose that this disk strikes a stick of length r equals 1.2 meters, and this stick has a mass of 2 kilograms. We're going to suppose that it strikes this stick at one end of the stick, and that the other end is nailed to a frictionless surface. Okay, and so this is going to mean that our stick can spin, and we're going to assume that this collision is a perfectly inelastic collision, and so they stick together and they start to rotate together, and they're going to rotate because one end of the stick is nailed down, and we can see this setup shown below here, right? So we have the stick, and we have it nailed down at one end, and our disk moving in with some initial velocity v is going to strike the stick at one end, and we're going to end up having the disk in the after picture here sticking to the tip of the stick, and the whole system is going to start to rotate about that pivot where we have the nail, right? And I guess maybe more accurately I could call this omega prime, because that would be our angular velocity after the collision. Okay, so this is the setup. And so what do we want to take a look at? We're being asked to find what the angular velocity of the two is after the collision. In part B, we want to find the total kinetic energy before and after the collision. And in part C, we want to know what the total linear momentum before and after the collision are. So let's take a look at each of these individually. Maybe I will copy down the variables here just so I have them. So we have the mass of the disk at 0.05 kilograms. We have the initial velocity of the disk at 30 meters per second. We have the length of the stick at r equals 1.2 meters, and the mass of the stick at 2 kilograms. Okay, so let's start setting up part A here. So in part A, we're going to definitely need another page. But for part A, we're going to be applying conservation of angular momentum here. So what is conservation of angular momentum? Well, we talked about it just last video. Remember that means that L is equal to L prime. Our initial angular momentum is equal to our final angular momentum. We can substitute in, again, because we know that L is equal to I omega, we can substitute in that left-hand side will become I omega, and our right-hand side is going to be I prime omega prime. Okay. And we also know that for a point mass, so initially, what is our I going to be? What is our moment of inertia going to be? Well, we know that for a point mass, I is equal to mr squared, right? And this is for a point mass. Okay, so that's our initial moment of inertia, and we also know that we can write our angular velocity in terms of our tangential or linear velocity as follows, right? So if I substitute in both of these equations here for the left-hand side of our conservation of angular momentum equation that we have over here, we're going to end up with the following equation, right? We're going to end up with mr squared v over r is equal to I prime omega prime. And we can clean that up a little bit, just cancel out the r in the basement there with 1 on top, and we're going to end up with mrv is equal to I prime omega prime. Okay. But what's I prime? So I prime is our moment of inertia after the collision. And we know that this is a perfectly inelastic collision, so we're going to have the two items, the two objects here, sticking together and then moving off together, right? So we really have to consider that and maybe I'll draw a line here. We really have to consider that I prime is going to have to be the moment of inertia of our stick plus the moment of inertia of our disk, right? So we've already said that the moment of inertia of our disk is and maybe I won't write it like this, maybe I'll do it like this. I'm going to leave a little bit of space for the moment of inertia of our stick, but we've already said that the moment of inertia of our disk is going to be well approximated by the moment of inertia of a point mass at a radius r. So that's the disk part. And the stick part we can look up in any table, maybe the table that we talked about a couple of videos ago now. And rotating a stick about one end of the stick results in a moment of inertia that we can write in this form. Okay, and this is the moment of inertia contribution from the stick. And remember, so I prime is both of these put together because we have the stick and the disk, which is now stuck to the stick, both rotating together afterward around that pivot defined by that nail that's driven into one end of the stick, right? And so we have this expression. Maybe I'll rewrite it once. We can simplify by pulling out an r squared. So I'll do that. We're going to end up with m plus capital M over 3 r squared. Okay, I'm going to box that off, and let's substitute that back into our expression that we have going over here. So this means that we're going to end up with m r v is equal to m plus capital M over 3 r squared, and we still have this omega prime over here. But let's remember that we're looking for omega prime because we want to know what the angular velocity of the system of two objects is after the collision. So let's solve for omega prime. So this means that omega prime is going to be equal to and I guess I won't skip any steps here. We could cancel out 1r here, or maybe because I'm short on space I will. So imagine that we're canceling out one r from over here and one from over here, and then I'm going to divide through by the bracketed term here. So we're going to end up with mv over m plus capital M over 3 r. Right? And if we substitute in numbers for that, I'll do that here from above. We know that our first mass is 0.05. Our initial velocity was 30 meters per second. Then we have 0.05 again, plus 2 over 3, and our radius was 1.2. Right? If we do that that calculation, we're going to find that omega prime is equal to 1.74 radians per second. Okay, and so that would be the answer to part A. Okay, so we've used the tools we talked about in the last video, and we were able to get the angular velocity after this collision. We also had to use some of our previous knowledge about inelastic collisions, and so we have our result here. In part B, we want to calculate what the total kinetic energy before and after the collision are. So let's do that. So part B, I have numbers worked out here. So in part B, well, initially we're going to have the initial kinetic energy. Only the disk is moving initially, so we expect that all the kinetic energy is going to be translational kinetic energy, right? So we expect that all the kinetic energy is going to look like this, where m is the mass of our disk and v is its initial velocity, because the stick originally is not moving, right? And so right away we can substitute in numbers. We end up with an expression that looks like this. And if we solve, we're going to find that the initial kinetic energy is equal to 22.5 joules. Okay. What about the final kinetic energy? Well, I guess first, what do we expect that we're going to find in the final kinetic energy? We have a perfectly inelastic collision here, and we know that energy is not conserved in that type of a collision. And so let's see what we're going to find here. We would probably expect that we would have less kinetic energy after the collision. Let's see what we actually find. So kinetic energy final, so after the collision, these things are both rotating around the pivot, right? And so we're expecting only to see rotational kinetic energy. And we can write that as 1/2 I prime omega prime squared, right? So I prime being our moment of inertia of both of these objects together. That's the I after the collision, and then omega prime being our angular velocity after the collision. We just solved for what omega prime is, so we're going to make use of that, and we also have an expression for I prime up here, so we can substitute that in. Let's do that. We're going to end up with 1/2 m plus m over 3 r squared, and we have our 1.74. This is our omega prime. It comes in squared as well. Okay. Let's substitute in numbers for these. We're going to have 1/2 0.05 plus 2 over 3. It's going to be 1.2 squared times 1.74 squared. If you put that into a calculator, you will find that the kinetic energy final is equal to 1.56 joules. Oops, that looks not like a J. Okay, so that's our final kinetic energy. And so we can see here that yes, a bunch of kinetic energy is lost in that collision, and it is in fact lower, obviously, after the collision. All right, so part C, I'm looking here. I think I have numbers. I do. So let's do part C here. Okay, in part C, we want to know what the total linear momentum before and after the collision are, right? So linear momentum before the collision should be pretty easy for us, right? The only thing moving before the collision is the disk, and we know that our linear momentum can be written like this, where again the only mass we're considering is the mass of the disk, and the initial velocity of the disk is the only velocity we're interested in. Right away we sub in numbers. And if we do that calculation, we're going to find that our initial linear momentum is equal to 1.5 kilogram meters per second, right? Simple enough. Now, what is our linear momentum after the collision? Well, again, I guess we could ask, what do we expect? Do we expect that our linear momentum would be larger or smaller after the collision? We may think smaller, right? This thing is having a collision. Maybe some of it's lost. Maybe we have conservation of linear momentum here. But I think that the result that we're going to find will be at least somewhat counterintuitive for some people. So let's go through here and see what we actually end up finding, and then talk about why the result is the way that it is. Okay, so linear momentum after the collision. Well, we know that the disk is going to continue to move, right? So it strikes the one end of the stick, and it continues moving, albeit on a curved path now, but that doesn't mean it doesn't have linear momentum. So we have m, and we have some v prime, right? So the velocity of this thing after the collision. We don't know what that v prime is yet, but we're gonna find that we don't need to solve for that v prime. We also are going to have the linear momentum of the stick, right? So the stick, again, it's moving on a curved path, but that doesn't mean it doesn't have linear momentum. It's going to have some linear momentum. And what is that linear momentum going to be? Well, it's definitely going to be based on its mass, and it's going to also be based on its linear velocity. But we have to think about its linear velocity as the center of mass linear velocity. So what does that sort of mean? I'm going to write it in here, and then we can sort of talk about what I mean by that. So I'm going to write VCM. And what is the center of mass velocity? So imagine, I'm going to do a little aside thing here. Imagine that we have our stick here. It's nailed to the table at one end, and so the disk hits this side of it, and the tangential velocity at this edge is some v, right? But the center of mass of the stick, assuming that the stick has its mass evenly distributed over its full length, which it does, the center of mass of the stick is going to be somewhere here. So we're really going to be interested in the velocity of that center of mass, right? So this is going to be the VCM, okay? And we're interested in what the velocity of that center of mass is, because that is where the center of this mass that we're considering in this momentum equation sort of resides. So we need to think about what the velocity of that center of mass is to be able to extract this contribution to the linear momentum, right? And so I guess we can think about it this way, or if we want, we can sort of think about it more in terms of an equation, right? So think about it like this: if we have some velocity, which we know we can write as r omega, right, where this is our radius times our angular velocity, then it must mean, or well, I should have probably come to the punchline here in the top part before I start talking about this. Okay, so put this bottom part on hold, and then if so returning to this top picture, if we think about the center of mass velocity, well, if it's halfway down the pole or the stick or whatever we have here, we can think, well, it's halfway down, so it's moving about half as fast as this outer edge would be. And if the outer edge is moving at v, then it must be true that VCM must be equal to v over 2. Okay, and this is sort of just a way to think about it, sort of diagrammatically. But now we can also apply some equations to this. So that's what I'm trying to do down here in the second box. So we start off with our expression that relates linear velocity to our angular velocity, and then let's write this down. So we have some velocity and some r and some omega, right? What if our velocity that we're looking for is the center of mass velocity? Well, that's the center of mass velocity, and that velocity is happening at a radius r over 2, right? It has to be true that if this is r and the mass is evenly distributed over the rod, then this must be r over 2 for the and that you can't really see that. Then that must be r over 2 for the distance from the pivot to the center of mass, right? And so if we're looking for some velocity at the center of mass point, which we know is at a distance r over 2, well, we just hit that with omega also, right? So we still have the same equation. We're just substituting in, instead of r, we have an r over 2, and that's going to give us our velocity at the center of mass. And so, and I should have primed this, I just noticed. And so, what does this mean? Well, this means that our v center of mass prime is going to be equal to r over 2 omega prime, right? Except that we know that we can write our omega prime as v prime over r for the same reason that we can write this equation up here. It's basically just a rearrangement of that equation up there, and we're priming the velocity and the angular velocity, right? Sorry, I have something going off here. Okay. So if we make this substitution, then we can write that our VCM prime is equal to r over 2, and our omega prime is equal to v prime over r, right? And so we can cancel out these r's, and we end up finding that VCM prime is equal to v prime over 2, okay? And that's exactly what we're kind of looking for here. We just want to write down our VCM in terms of v, because we already have our velocity in this first term here, right? So let's make that substitution. Let's substitute in VCM prime for v prime over 2, and we end up with p prime is equal to m v prime plus capital M v prime over 2. Right? Okay, so we can now simplify this a little bit. We can clean this up. So we're going to end up with p prime is equal to, I'm going to factor out our v prime, and we're going to end up with m plus capital M over 2 v prime. And again, I'm going to make use of this equation that relates our tangential velocity to our angular velocity, and I'm going to let v prime equal r omega prime. So let's do that, and we're going to end up with p prime is equal to r omega prime m plus capital M over 2. Okay, and at this point we know all these variables. We just calculated what omega prime was. We know what r is. We know what both m's are, and so we can substitute in and solve for this. We find that p prime is equal to 1.2 times 1.74 times, what is that going to be, 0.05 plus 2 over 2. And if we clean this all up, we're going to find a p prime equal to 2.19 kilogram meters per second. Okay. And so what have we found here? Well, we found our final linear momentum, and we already had found our initial linear momentum. And somewhat, maybe surprisingly or counterintuitively, it ends up that our final linear momentum is greater than the initial linear momentum we had. And how do we sort of think about this? Why is it that p prime in this case should be greater than p? Well, it turns out that the nail, the sort of setup of the problem is sort of what's doing this, right? So just really quickly think about it like this. We have our stick here, and it's kind of nailed down here, right? We have this this disc crashing into the top of our stick, and it's applying some sort of, we can call this the force applied by the disc to the top of the stick, and it's causing this thing to start rotating, right? But as it smashes into this thing, the nail has to stop the whole thing from moving, right? The nail is applying a force in this direction, the force of the nail, let's call it, and it's this force of the nail, the force the nail is exerting at the bottom of the stick, that's really giving us this additional momentum. Okay, and it's not super obvious when you think about it originally, but when you think about the nail in this case, it kind of brings it into focus, right? And so that's basically it for this problem. There's a number of other two-dimensional rotational collision problems that we can do. I'll probably put one on the assignment, but it's a good class of problems, so make sure you can do them. Try to do some extra ones from the textbook, and that'll pretty much close it out for this set of videos. And I'll see you guys in the next one.